right. Hi, Verge.
Hi, Mark. Hi, everybody. Thanks for coming back and joining us for another AP Live.
All right. And I guess we should move along. Let's see if I'm having troubles. All right. There we go. I am Mr. Mark Corrali from Billy Ryan High School in Denton, Texas.
And I'm Verge Cornelius, and I teach at Lafayette High School in Oxford, Mississippi. We're so happy that you're joining us for our 5th AP Live session. And let's see what we're doing today.
All right. So this week we are finishing up differential equations. We've gotten through slope fields. They are going to gently recede into the background as we move on to solving differential equations and really spending the rest of the week on 7-7 and 7-8. Although 7-6 is rolled in there and 7-5 and 7-9 are BC topics. Next week, we will do Unit 8, and while we know Unit 8 is not tested on this year's AP exam, we are going to tie it back to previous units. So that'll be that next week in April. And then for the remaining 3 weeks, isn't it? We will review all the 2020 tested topics in addition to some test taking strategies. And we're all looking forward to Friday's announcements of exactly what the test is going to contain. Verge, you want to take this since you found it?
Sure. So this is our daily corrections and oversight. This is a new feature where we're going to talk about any mistakes that we had in our prior video. And we didn't get any emails, messages, phone calls, anything about yesterday's video. Wow. And then when Mark and I were prepping this morning, I actually noticed an error on number 7, which happens to be the warm up that we're going to do. And if you downloaded those documents out of the Dropbox yesterday or this morning or whatever, we've actually gone back and fixed them all. Actually, I watched Mark fix them this morning, but it should have been dy dx, not dy dy. And anyway, it's now fixed in the Dropbox, and this in fact is going to be our warm-up for today.
And if you're wondering, dy dy usually is 1 because y changes really closely to itself. For some reason, oh, there we go. All right. So our introductions are out of the way, and I guess I should change that to introductions and corrections, huh?
That's true.
We're going to spend about 5 minutes on the warm-up, and then the 7-7, I will start, and then I will hand off to Verge, and over that 25 minutes, we will talk about using separation of variables to solve differential equations with some guided practice. For those of you that are more familiar with the CED, this is actually 2 sections in the CED. We're just rolling it into a 2-day lesson, but we're keeping the title 7-7 for the entire time. And then we'll wrap up and talk about what is in the Dropbox. I did put it in there already, so there were a couple requests that we put stuff in. It's really hard for us to get it in very early because we do gather in the morning and look over things like that dy.
And talk about our virtual backgrounds.
Yes, well, the important things.
So I Mark's right away today. I feel pretty impressed with myself.
It's rare I'll match the shirt to the background. So we'll let you know what's in that Dropbox, and if you want to pause us and go get those resources right now or whatever, those are in there. All right, so today's warm-up is the aforementioned number 7 from last night's homework. And I'm just going to reread it to you in case you didn't get a chance to look at it yet, or you're watching this at some later date. For each of the given differential equations, sketch the solution curve that passes through the point -4, 4, sketch the solution curve that passes through the point 6, 2, and sketch the solution curve that passes through the point -2, -3. And then the reason it's plural is this was the directions for 4 different problems. dy dx is equal to x over y, and the slope field is provided there. And for those of you that did watch yesterday's lesson, you'll know that it was creative with using my technology. So I did a little foreplanning this time. So I'm just going to advance.
We're going to give them about a minute to do this, Mark?
Oh, yeah.
Yeah.
Sure.
Okay, so we're going to ask you guys to take about a minute to do this warm up, or to locate, if you've already done it yourself, locate your notes. You can kind of sketch it out the way Mark showed yesterday on notebook paper, just on the side. What would this one look like? What would that one look like? What would the other one look like? The 3 different solution curves. And meanwhile, while I'm filling up airtime, we've got about 25 more seconds. I've got another joke for you. So this is a good one. What did the mermaid wear to algebra? Oh, I messed up.
Oh no! We are not putting that on the correction slide. We are catching it right now. So we have a 30-second delay. I don't know if they can cut that out. Hey, Verge, let me just ask you a question. You were talking about a mermaid, and was she going to a math class? What was she wearing?
She was wearing an algebra, of course. That's what mermaids wear to math class. All right, time for the warm-up answers.
Okay, something we may be a little better at. All right. So the first one we drew here, we drew the solution curve that passes through the point -2, -3, and you'll see we hit the point. We stay between these curves. Looks like it may even be getting asymptotic, getting through those slope lines on the way down. And if you're seeing my cursor jump, it's because my zoom controls are in the way. So next up, that one was pretty nice because it was a nice continuous function through the slope field. All right, next we went through the 0.62. So it goes up here to the right, again, towards that 45 asymptote. Maybe it should be a little steeper there at the end, but trying to follow those tangent lines. And when we get down here to the y-axis, or actually the x-axis where y is 0, we have this hole. And that's because when y equals 0, this definition of the derivative is undefined. And so that point is not in the domain of our original function, which is our derivative. Our derivative is a 2-variable function. And so the inherited solution can't include that point either. And lastly, we go through the point -44. We discussed this a little bit yesterday. I actually got some follow-up messages from some teachers, and I think I may have heard from one student. This is, hey, we've got this line. It's staying on those tangent lines with slopes of -1. And then when it hits the origin is not included. And we have to stop there because our solution function is a continuous curve. And that bothered some people. A lot of people wanted it to continue down over here. So let's talk about why that doesn't happen. So here's an example of a function, which I'm sure this is the first thing that jumped to everybody's mind when they saw the slope field, is this is the solution, right? So if we have a piecewise function that's defined y equals -x for x less than 0, and then the function is not defined at all on the open interval from 0 to 4 square roots of 2, but then picks up at x equals 4 square roots of 2 as the square root of x squared minus 32. If you take the derivative of both parts of this piecewise function, on the right side, this derivative does become x over y. It becomes actually it becomes x over the square root of x squared minus 32, which for that fork is y. And for the left fork, the derivative is just -1. But if we look down here, I've kind of said, well, for x is y, if y is -x, then that function that derivative is going to be -1. So this function that's represented by this blue and this green could be a solution to this differential equation. And that's why this needs to be open and stopped, because frankly, since the only point we were given, excuse me, was that point -44, I really don't know what's happening on the right. This might be happening. It might be the line continuing through. It could be any of these other pieces of hyperbolas over here. It actually could be an absolute value function, the derivative. No, I'm sorry, I take it back. Absolute value function with just x not being allowed to equal 0 would also satisfy this as a solution curve. So don't worry about that too much. You're not going to have to find stuff like this necessarily, but we just wanted to address why that was happening. But our friend Verge today is going to take over and tell us how could we find parts of this at least.
I won't take over quite yet, but we do have a couple of slides before I go to my overhead, and these would be great to just take a screenshot of. What happened to those slides, Mark? You know what I'm
They're
talking
coming.
about? Yeah, okay. Yeah, these are, we just wanted to do a little nod to the difference really between a general solution of a differential equation and a particular solution of a differential equation. So how do we compare them? What's the difference between a general solution and a particular solution? So we created this kind of comparison here. If you had a differential equation such as dy dx equals 2x, you can go ahead and take over, Mark.
Okay, so if we have our differential equation is 2x, and what we're asking, we're trying to find a solution. Again, we could sketch this and look at the slope field, and it would look like a family of parabolas, because 2x is the derivative of what? And at this point, Verge, what do you believe 2x is the derivative of?
It's the 2x is the derivative of x squared. I mean,
Right.
I taught that to my own child, when he was 3 years old. It's a great party trick.
So,
But it's the derivative of x squared and also other x squared plus 5, for example. It's a derivative of x squared plus 5.
right, and this x squared plus 1 is definitely x squared plus 1, x squared plus 5, x squared minus 7. We don't know, because that plus c, what is, trying to remember from algebra 2, Verge, what does plus c do to this graph?
That's that vertical translation, moves it up and down. So it because of the nature of that particular kind of function, that's what happens when you add something to it.
And that vertical shift is not going to change the slope at any of those x values, since this thing is only dependent on x. So this is a whole family. And so we talk about the general solution. This is kind of the slope field. This is all of the whole family with all these different constants added in. But if we talk about a particular solution, and now we're talking about going through -2, 5, well, now we're looking at y equals x squared plus 1, because if I stick -2 in there, -2 squared is 4, and 4 plus 1 is 5. Now that is the curve that passes through that point and has a dy dx of equal to 2x. And then we just threw a couple more here to show you. So 3 that's a constant slope. So that's just the linear function 3x plus c, but it's any line 3x plus c. And I guess you could use a little b there if you wanted, if you're a slave to the mx plus b family of functions. And again, to go through -2, 5, I believe it's 3x plus 11. Let's see, 3 times -2 is -6 plus 11. I think that's 5. We will find out tonight if I'm
Make a
wrong.
mistake on that one.
All right, so moving on, just a last case, and this is one of them that was in the review assignment from yesterday, is this -x over y. Sorry, I don't know if you can hear that in the background, but my 4-year-old just came into the room looking for toys. Okay, I have to stop this for a second to give my daughter a hug. Okay, say. All right, now can you go back to mama? All right. So that was unplanned. -x over y. The general solution to this, in version, I talked about this, and I know Brian Passwater, who's doing the BC review videos, doing half of those, he and I have talked about this as well. One of the issues we have is the general solution is supposed to be a function. And neither of these are functions, because until we have a point, we can't really decide where the solution belongs. So we get this y squared equals -x squared plus c, which is a nice relation that we can solve for y, but we have this choice of plus or minus, because we know it's semicircles, but we don't know whether it's top halves or bottom halves until we get a data point. And then once we have particular solution through -2, 5, well, now if I stick a 2 in there, we get 429 minus 425 squared 25. Whew. All right. And so here's our semicircle that goes through -2, 5 and would fit in that slope field very nicely. Again, the endpoints are undefined because we don't know what's happening there. They're either not differentiable or they may not even be included in the domain of the solution. Questions, Verge?
No, I think if you're watching, this slide right here is actually much harder than what we're going to do today. This is just
Oh,
kind
absolutely.
of where we're going and how we're able to come up with those general and particular solutions. We're going to learn the procedural, get better at the procedure for it, basically.
And that's where I'm going to hand off to Verge. She's going to start telling you guys, like, where did this come from? How did they jump here so fast from here? And we didn't jump there really fast.
Yeah.
So you want to grab the
Okay, so I'm
screen?
going to go ahead and grab the screen right now so that I know. Here we go. And this is my little sticky note to myself. It is Tuesday. This is our 5th AP Live, and we are predominantly working on section 7.7 right now. And 7.7 says that we are trying to find solutions to differential equations. Some differential equations can be solved by this technique of separation of variables. And there's actually many differential equations that we consider non-separable. And for AP, we do not worry about those. We worry about those in an entire semester class in college called differential equations. So the ones that we are going to solve today and tomorrow and Thursday and Friday, as we're reviewing and practicing, are all separable differential equations. Anti-differentiation is going to come into play here because how we are going to find those solutions is by anti-differentiating, kind of going backwards, thinking about what could the original function have been. So the materials we're going to use today that you apparently, Mark, you said you already put them in the Dropbox.
Yes.
Is that right? Okay. So
and as long as you're doing that, because instead of texting my friend here back who sent me something, I'm going to just go ahead and address it. And let me get the name. Sorry. Because I'm sorry, I'm going to have to give proper credit tomorrow, but a colleague that teaches in Birdville High School here in Texas sent us a separation worksheet, and there are some rendering glitches on it. There's just some empty boxes that you have to ignore. That's because she wrote that in Google Docs for another entity, and so when it got translated into Word doc, but basically just read those boxes as blanks and everything will be fine.
Okay, so in the Dropbox, there's actually 4 different things in the Dropbox for today. And one of the things in the Dropbox is a circuit that Mark wrote that I had never worked before we were preparing for these lessons. I think I worked it maybe on Sunday or something for the first time. And if you don't know what a circuit is, boy, are you in for a treat, because these are so much fun. The idea is that you're going to go ahead and work the problem, and then you look for the answer, and then that becomes your next problem. So what I've done is I've actually cut up this particular circuit here, and we're going to just work them kind of one at a time. So this one says solve for y, and I'm given dy dt is equal to 2t. So what that means is that I need to separate my variables, and then I need to anti-differentiate. Now, different teachers are going to do this slightly different ways, but I think what I'd like to do is show you the separation of variables right off the bat. In other words, I'm going to move this dt, this differential, to the other side and get it with the 2t, and then I'm going to anti-differentiate. So what that looks like is dy is equal to 2t and then dt. Integrate on both sides. The integral of 1 dy would be y. The integral of 2t dt would be t squared. And then this idea of the plus c would come here on the right-hand side. Now, I might say...
Oh, I was about to ask.
Of course you were,
Why isn't there a C on the left side, Verge?
Right. Well, actually, there's a kind of like a C1 and a C2, like a thing 1 and a thing 2 from Dr. Seuss. But generally what mathematicians do is they just lump this C all together on either one side or the other. I tend to do it on the right-hand side. But yes, when we integrate this dy, we get y plus C1. And when we integrate on this side, we get t squared plus a different C. You know, when you actually combine these together, you get just that single C. Okay, so we get y is equal to t squared plus C. That is the general solution to that differential equation. And then what Mark has here, he wrote this circuit. He says, find a function that might be y. There's 12 or 16 problems here, so you have to kind of search around and find something that might be the same as y. And I've already done it. kind of like Julia Child. Here comes the turkey out of the oven.
Out of the other oven. Yes. By the way, for anyone that's not a teacher, Julia Child would have been on the Food Network had it existed in the 70s. Just a
Yes, yes.
40-year-old, 50-year-old reference there.
And she and I both went to the same college, although at different times.
Verge, can I interrupt before you start number 2?
Well, you already are, but go on.
Yes. May I continue to interrupt?
Yes.
For that, I'm stealing your screen. All right. I just want to say, because I know there's going to be a couple emails from teachers that are going to say, but you don't multiply the DT over.
Okay.
So our friend Leibniz, right? Great. Do you have a T? I always want to put the T.
That doesn't look right to me, but it's okay. That looks better.
Gottfried. Let's just okay. He was brilliant. This differential notation was his. This is actually the definition of a differential, which is not in our course anymore, although it's in lots of our textbooks, and I know many of us still teach it. And the differential of y is defined as y prime times dt. So the jump that you're making when you do this is you're plugging your derivative, which is dy dt, into this differential equation. It is not a big deal. Leibniz did this brilliantly, so it looks like we're multiplying both sides by dt. You can absolutely think of it that way. When I talk about it, I always refer to it as garbage math, but it's good. It's good garbage math because you can see where the dt's would cancel if this was actually a true fraction. Again, I'm doing this just for technical purposes because there's going to be 1 or 2 people who are like, you can't multiply by that, and so I just wanted to address that.
Okay, thank you. I'm going to try and grab this back.
If I keep doing that as the week goes on, Wikipedia says either spelling. Thank you, Nicole from Minnesota.
All right, so this answer right here, which led me to the second problem, is of the form y equals t squared plus c, it's y equals t squared plus 8. So here's my second differential equation. Again, I'm prompted to solve for y. I have dy dt is equal to 1/2, and separate. So I get dy equals 1/2 dt, and then integrate on both sides, which is tantamount to anti-differentiating. The integral of dy would be that y plus c. Remember, that's a 1 right there. So think about, well, if the derivative is 1, then the antiderivative would be y or x or whatever that variable is with your differential, is equal to 1/2 t, and then plus that c where everything is lumped together. So that's my second one. That's my solution, my general solution to that differential equation. And that becomes my third problem. So my third
again, she's looking for that answer at the top there.
Yeah. So that's exactly right. So I've got y is equal to 1/2 t plus c. That's my general solution. And here is a function that might be y. Y is equal to 1/2 t plus 7, where my c value is 7. Okay. Looking at number 3, I have a new differential equation. And again, it says solve for y. It's dy dt is equal to 1/2 t. So I separate. Dy is equal to 1/2 t dt. And then I integrate. The integral of dy ends up being y. The integral of 1/2 t. Now this linear term has to go up a notch and become quadratic. So I have to add 1 to that exponent and divide by my new exponent. So that ends up becoming 1/2 times 1/2 t squared plus c. I don't really show it like this. I don't do it like this myself. I just want to kind of show you what's happening. The 1/2 is right there. And then the 1/2 t squared is the antiderivative of t to the 1. So when I multiply these two together, I end up with 1/4 t squared plus c is equal to y.
Hey, Verge,
Yes, sir.
what if they brought the 1/2 out front of the integral?
That'd be good.
But then you'd have half a c.
You mean like, um,
I'm just,
yeah. Are
I'm
you
being
gonna tell a
ornery.
joke right now, or are you gonna say like if you still put water in the sea, it's still the ocean or something?
Yeah, it's kind of getting to that idea. Yes.
I'll do that. I'll do that on number 6 when we get there.
Okay.
Yeah,
Excellent.
slide
Excellent.
that coefficient out. That's what you're talking about?
Yes.
Okay. I like it. Okay. This next one here, number 4. Oh, by the way, I should do this. Hold on a second. I know that this is my next example that I'm going to do because I have this form y equals 1/4 t squared plus c. And as I look at this answer, y equals 1/4 t squared plus -2. So this c value is actually negative in this case, and that's totally fine. All right, so this time I have, I'm going to solve this differential equation. Dy dt is equal to t squared. So dy dt is equal to t squared. I'm going to separate. So I get dy is equal to t squared dt. And then I'm going to integrate. Integral of dy is just y. Integral of t squared is going to be add 1 to my exponent, get 2 plus 1 is 3, divide by my new exponent. That's the reverse power rule. 1/3 plus c. What's the matter?
You lagged out for a second. But...
Oh, okay. So let's see here. SEE. Y equals 1/3 t cubed plus c. Y equals 1/3 t cubed plus a -4. That's in that same form. So that works. Uh-oh, we got a good one here. Solve for y. Sometimes you'll need to factor to help separate. Okay, so I'm ready for this. It says dy dt is equal to 2ty minus 8t. And then it says this is the same as is equal to 2t, and then in parentheses y minus 4. In other words, the 2t got factored out by that greatest common factor. So what's happening here is I'm going to go ahead and solve for y. I'm going to solve this differential equation, but I'm going to, when I write it down, I'm going to write down the factored form.
And if you're wondering why I included the factored form on this worksheet, when you go in the Dropbox, there's actually 2 pages in the front, which I recommend not printing, that is a blank page for notes, a summary of how to do these early separation variable problems, because I wrote this for a day when I was going to miss class for some reason. And so if you're wondering why did he give him that? Well, this is the first time my students had seen it.
Okay, so there's my differential equation with the 2t factored out. So then I need to do the step of separating. So this y minus 4 has got to go up underneath this dy, and this dt over to the other side. And Mark, he was talking a little bit about we're not really dividing both sides by y minus 4 or multiplying both sides by dt. But this is the correct separation here.
Yes.
Now, this, when I anti-differentiate, the right-hand side is not too bad. I think especially polynomials, it's pretty easy for us to see what's going on. So for that integral of 2t dt, I would get t squared plus c. On this side right here, I have to recognize this is a natural log. So the integral of dy over y minus 4, I might think of that as the integral of 1 over y minus 4. I know my students appreciate when the differential is kind of on the side there. And this right here is really, somebody took the derivative of a natural log. You can think about a U substitution if you want, but it's not necessary because this is just a linear divisor with a coefficient of 1. So there's not going to be any chain rule that was involved or anything like that. So we usually just hop straight to the natural log of y minus 4 in absolute value, and that would be our antiderivative. This is a case where I would have to definitely solve for y, so that's going to take a little bit of effort. I would exponentiate, so I get e to the t squared plus c. The c is up in that exponent, and then absolute value of y minus 4 is a result of e to the natural log of y minus 4 in absolute value.
E to the t squared plus c, right?
Yep.
Oh, I see what you're saying. I see what you're saying.
Yeah.
Yes.
I always do the easy side first.
Yeah.
Well, okay. Yes, I always do the easy
No,
side first.
I got you.
Okay, so removing the absolute value bars requires a plus or minus on the other side, since the absolute value is the positive and the negative. And then to finally solve for y, I would add 4 to both sides. So I would get y is equal to 4 plus or minus e to the t squared plus c. And that t squared plus c is all up in the exponent. I'm going to circle that because when I look for it, something of that form, it actually doesn't look quite like what I have circled. And remember, we're trying to find a solution, a function that might be y. So we don't have any information. That's going to be tomorrow's lesson. We don't really have any information about how to find that c value because we don't know a point that's on this solution curve. But if I look here at this answer is definitely of that form. We've got y is equal to 3 e to the t squared plus 4. And here I have 4 plus, so I would have picked that branch perhaps, 4 plus e to the t squared plus c. So this definitely is the correct answer. And the reason is, just to go a little bit algebra 1 on us here for a minute, this part right here, e to the t squared plus c, just this part, I can write this as e to the t squared times e to the c, because if the bases are the same and you're multiplying, you can the exponent. So I'm like splitting that apart instead of condensing it. And then e to the c right here.
Wait a minute, e's a constant.
Yes.
Yes. I'm just trying to help you out.
Yes. Well, right. I mean, e to the c is just, e is a constant to a constant is a constant. So e to the c is just another c. So that's why here it can be written as a coefficient. So like e to the t squared times c. So I could even write this as y equals 4 plus or minus c, which would be a different value of c actually than the c up in the exponent, e to the t squared. This is very common with exponential functions. So the one that it matched with was this 3 for my constant, and then e to the t squared, and then plus the 4. When Mark writes his circuits, and we're both writers of circuits, when Mark writes his circuits, he tends to do things like this around problem number 5 that are very challenging, which is interesting to me. I always get surprised by it, but it's good because it's like, whoa, I just did that really hard part of the workout. And now look at this gift I have. Look at this one that's not sad. It just doesn't seem nearly like that other big amount of work that I just did. So let's try this one. This is our number 6, if you're numbering them in your notes. I got to find some clean paper here. Number 6, if you're numbering them in your notes. And it says solve for y. Differential equation, dy dt is equal to 2y.
And I just want to interject here, because now at the bottom it says to find a function that might be y. When we say a function of y, we do mean in terms of x, because or in terms of t in this case,
Yep.
because I'm sure someone out there is like, well, you just divide both sides by 2 and you solved for y.
True. True.
So understand with the differential equation, when we say solve, we're saying find a solution curve with this differential equation.
And there's anti-differentiating involved for sure. So in this case here, to do the separation, my strategy is I generally leave any coefficient over with the independent differential. In other words, I would leave that 2 there with the dt, and then I would divide both sides. Well, I mean, it's like you're dividing both sides by y, but I would have dy over y is equal to 2 dt, or in fact, 1 over y dy is equal to 2 dt. And the reason I do that is that my work becomes a lot cleaner in the long run. I don't have to worry about as much u substitution or chain rule gone bad or whatever if I leave that coefficient over there. What about you, Mark? Do you tend to do that too? Do you tend to leave everything?
Yes, and early on, I'll even write the 1 in if there isn't a coefficient over there.
Okay. Yeah, it just will make your work a little bit less error prone, basically, more efficient. All right, so here we go. We're anti-differentiating. The integral of 2 dt is going to be 2t plus c. And then the integral of 1 over y dy is going to be the natural log of y plus some other c value. But like we said, we're lumping them all into that just general c. Exponentiate. Again, I'm doing that because I'm trying to, I have to do kind of the inverse operation here. So I'm trying to get rid of this natural log. So I exponentiate, I get absolute value of y is equal to e to the 2t plus c. And then y is equal to plus or minus e to the 2t plus c. Again, because the exponential function, we tend to write that c in front. And this solution right here, or this function that might be y, is no exception. It says here y is equal to 5 e to the 2t. That's got to be my function that might be y. 2t up in the exponent there. And then this e to the c ends up being this coefficient of that function. Next one is a great one for you guys to try. This says solve for y. dy dt is equal to 2.
And you might want to move your work out of the way in case someone faded out and comes in and thinks that work is, because that 2 is.
So we're looking at number 7. One for you to
Not
try.
that anyone would ever fade out on our videos. We're watching.
Hey, I saw somebody posted yesterday that there were cats that were actually watching our videos.
Yes.
I think
the video I saw posted, it was right when my software glitched and put a text box up. So that was.
All right. So for dy dt equals 2, I would separate, get dy equals 2 dt, integrate, so I get y is equal to 2t plus c. I don't have to solve for y or anything because it already is isolated. So I would just go ahead and search for my answer. We're looking for a function that might be y. And here it is, y is equal to 2t plus c. Oh, y is equal to 2t plus -5, where the -5 is the c value.
And you were saying how I throw a hard one in there and then I back off. This was backing way off.
I was backing way off. Like, yeah, definitely way off.
All right, we're at about 6 minutes left. Do you want to let them work on another one?
Yeah, well, I don't know. This one seems so different, so I'm a little worried about.
No problem.
I think I might you know, those of you who are speedy probably could work it faster than I could. But we've got dy dt is equal to 3t divided by y. So separate, I would say y dy is equal to 3t dt, integrate. Integral of y dy is going to be, integral of y dy is going to be 1/2 y squared. Integral of 3t dt is going to be 3/2 t squared plus c. Oh, Mark, this is one where it would have been nice to throw this 3 outside of the integral.
Well, we can actually cover it here when you get rid of that half on the right as well. Yeah.
Yeah. That Mark loves doing this. So like if I multiply both sides by 2, and now I really do have to solve for y. If I multiply both sides by 2, I end up with y squared is equal to t squared plus 2 times c. What is that? C.
If you double the size of the Red Sea, it'll still be the Red Sea. So
yeah, if you just kind of double the C, it's still the C.
Now I know it is an arbitrary constant, which is why we're allowed to do this. Your instructors, your personal instructors, when you get to Cal 2 or Cal 3, they may want you to differentiate those C's, to not to totally use a horrible calc pun. But so if someone says you should have a C1 and a C2 and a C3, then do what your instructor asks you to do. But in this case, you know, we feel it's an arbitrary constant, and there's a group of people who agree with us that until you actually apply a point to this, that C can just keep absorbing whatever it needs to absorb and remain the C.
Exactly. We're going to go ahead and solve for y here. Take the square root of both sides, and y ends up being plus or minus the square root of 3t squared plus c, and that would be that general solution. But as we look for one that might be y, this one, y equals negative the square root of 3t squared plus 9, that's definitely a particular solution going through some point that we didn't know about. So we are going to kind of end on that one. There are just a few more of this circuit for when you go to the Dropbox. I'm going to go ahead and, Mark, you can go ahead and grab the PowerPoint back again. Again, there's 4 things in the Dropbox today. So you can have that, get that circuit. You can get the separation activity that somebody shared with us. You can get answers from yesterday's lesson. What was the last one that was in there? Or maybe that was it.
Let's see, so there's, I could pull it up. I'm gonna do, can you still see the PowerPoint slide? Okay. I always get nervous when I open something. If you get a gray box or something, I apologize. So there's the key for yesterday's. There's a worked out key for yesterday's with that number 7 correction on dy dx. This circuit is session is called it, that TJ's, and again, I just don't want to mispronounce her last name, and so I want to look that up before I give full credit. Her differential equation separation practice, and then we had put that 4-corner quick skill review into yesterday's Dropbox, and the key for that is in there as well.
Right.
And that also gives you a preview of what we're doing tomorrow, because that 4th corner and that is finishing this with a particular solution.
That's right. All for the next lesson, it's all about finding that particular solution. And we would have to have just a little bit more information to do that. We need to know a point that's on the solution curve. And that's exactly what tomorrow's lesson is about. And we will carry that through even on Thursday and Friday. We'll keep doing more of those as we move forward. And I guess it's time to say bye. Don't forget to message College Board if you know of somebody who doesn't have connectivity or doesn't have a device. They want to help. They want to make sure that as many people as possible can watch these videos. So don't forget to take advantage of that and help each other out. We really miss our students a lot. Getting a little teary just thinking about it, but I know that they're working hard, and we really appreciate you coming and watching our videos and learning with us.
Yes, and yeah, and this is a neat opportunity. Unfortunately, neither one of us could do this if schools were in session, right? So
that's right.
We all miss our classrooms quite a bit.
Yeah, Thank you guys so much for being with us, helping
Ooh,
us
my
learn
hand's
this new
disembodied there. Thank you.
reality. I'm gonna go.
All right.
Bye.
Bye, Verge.